Good day, everyone. I am Jesse Cersola Savano, grade 11 STEM student of Mother Teresa Colegio de Balatan. Come and join me to explore and know why understanding the layers of the earth is important to Earth and Life Science. Entitled Journey to the Center of the Earth, a Scientific Exploration. The Earth is not just one big rock. It is composed with various layers such as the crust, the mantle, the outer core, and the inner core. Each layer has a unique temperature, substances, and purposes. By studying this layer, scientists are able to learn about such phenomena. Earthquake, volcanoes, and how mountains forms. These layers informs us about the past.
Mahirap naman kasi talaga ang magparaya, pero mahirap din ang hindi ipaglaban ang taong mahal mo. Kung papipiliin ka sa love story na gusto mo, ano ang pipiliin mo? Yung taong mahal ka na kaya kang ipaglaban hanggang patayan? O yung taong mahal mo na takot lumaban at handang sumuko na lamang?
Hey. And how Earth evolves over time. Ready to go on the thrilling journey to the center of the Earth? Let's dig deep and uncover what lies below. The first layer of the Earth is the crust. The crust is the outermost layer of the Earth. It's the surface we walk, build, and lived on. Compared to the other layers of the Earth, the crust is very thin, like a skin of an apple. But despite being thin, it is incredibly important because it contains lands, oceans, mountains, soil, and all life. The continental crust. The continental crust is thicker and less dense, primarily composed of felsic rock like granite, and forms the continents. Typically 30 to 50 kilometers thick but can be thicker under mountain ranges. Primarily composed of felsic rocks like granite, rich in silicon and aluminum. Less dense than the oceanic crust, averaging around 2.7 grams cubic per meter. Generally older than the oceanic crust, with some rocks dating back billions of years. Forms at subduction zones and collisional boundaries, often through recycling of oceanic crust. The oceanic crust. Oceanic crust is thicker and denser, made of mafic rocks like basalt, and lies beneath the oceans. Typically 5 to 10 kilometer thick, primarily composed of mafic rocks like basalt, rich in iron and magnesium, denser than continental crust, averaging around 3.0 grams cubic meter. Generally younger than the continental crust, constantly being created at mid-ocean ridges and destroyed at subduction zones. Created at mid-ocean ridges through volcanic activity and seafloor spreading. Characteristic of the crust. Brittle and solid, it can be cracked and break, especially during earthquakes. Divided into tectonic plates, these plates floats on the semi-soft mantle and constantly move. Movement causes earthquakes, volcanic eruptions, and the creation of mountains. Contains all the Earth's soil, rocks, minerals, fossil fuels, and natural resources. Importance of the crust. It is the foundation of life the crust holds. Soil for growing plants, minerals and ores we use for tools, buildings, and technology. Water sources like rivers and underground quarries. Fossil fuels like coal, oil, and natural gas. It plays a major role in geological activity and climate regulation. Example of crust features. Mount Everest, part of the continental crust formed by colliding plates. Mid-Atlantic Ridge, underwater mountain range formed where plates are pulling apart. The Mariana Trench, deepest part of the ocean, where one plate is sinking under the another. The Earth's crust may be thin, but is vital for life, natural resources, and geological processes. It's made up of continental and oceanic crust, each with its own characteristic. Understanding the crust helps scientists predict natural disasters, locate resources, and understand how the Earth evolves over time. The second layer of the Earth is the mantle. Mantle is a thick layer located between the crust and the core, primarily composed of solid rock. It is the largest portion of the Earth's volume and mass. On a geological timescale, the mantle behaves like a viscous fluid, influencing tectonic activity. The mantle. Location. The mantle lies beneath the Earth's crust and extends down to the core. It is separated from the crust by the Mohorovičić discontinuity or MOHO, and from the core by the Gunted Bridge discontinuity. Composition. Primarily composed of silicate rocks, the mantle is mostly solid, but its behavior on geological timescale is similar to the viscous fluid. Thickness. The Earth's mantle is about 2,900 kilometers or 1,802 miles thick, making up about 84% of the planet's volume. Significance. The mantle plays a crucial role in the plate tectonics, as the convection currents within the mantle drive the movement of the Earth's crucial plates. It has also influenced the formation of both oceanic and continental crust. The third layers of the Earth is the outer core. The Earth's outer core is a fluid layer situated beneath the mantle and above the solid inner core. It's primarily composed of liquid iron and nickel and responsible for generating the Earth's magnetic field. The temperature in the outer core ranges from 4,500 to 6,000 degrees Celsius. Composition. The outer core is mainly composed of liquid iron and nickel. It also contains trace amount of lighter elements like silicon and oxygen. Physical properties. Liquid state. Unlike the solid inner core, the outer core exists in a liquid state due to lower pressure and high temperatures. Temperature. The outer core is extremely hot with temperature ranging about 4,500 to 6,000 degrees Celsius. Thickness. It is approximately 2,260 kilometers thick. Location. It lies between the mantle and the inner core at a depth ranging from about 2,900 kilometers to 5,150 kilometers. Role in generating Earth's magnetic field. The movement of the liquid iron and nickel in the outer core, driven by the convection currents, generates electric currents. These electric currents produce the Earth's magnetic field, which extend through the mantle, crust, and atmosphere. This magnetic field is crucial for protecting Earth from harmful solar radiation and cosmic rays. The fourth and last layer of the Earth is the inner core. The Earth's inner core is the planet's innermost geological layers, primarily composed of solid iron and nickel. It is a hot, dense sphere with a radius of about 1,220 kilometers or 758 miles. The intense pressure, even higher than the melting point of iron, keeps the inner core in a solid state. This solid inner core plays a vital role in generating and maintaining Earth's magnetic field. Composition and structure. Solid iron and nickel. The inner core is predominantly made of iron, around 80%, and nickel, similar to the outer core, but the immense pressure prevents it from melting, according to National Geographic. Radius. The inner core has a radius of approximately 1,220 kilometers or 758 miles. Spheroid shape. It is not perfectly sphere but is described as a spheroid, a shape that is not quite round. Temperature. The temperature at the center of the inner core is estimated to be around 5,200 degrees Celsius or 9,392 Celsius Fahrenheit. Pressure. The pressure in the inner core is incredibly high, estimated to be nearly 3.6 million atmospheres according to National Geographic. Crystal structure. The iron crystal in the inner core are thought to be arranged in a hexagonal closed pack or HCP pattern, aligned along the Earth's axis of rotation and magnetic field. Function and significance. Magnetic field generation. The inner core's interaction with the liquid outer core is crucial for generating the Earth's magnetic field, a phenomenon known as the geodynamo. Earth's dynamo. The inner core's rotation slightly faster than the Earth's surface, and its interaction with the outer core are essential for driving the geodynamo. Recent discoveries. Changing shape. Recent studies suggest that the inner core may be changing shape, possibly due to interaction with the liquid outer core, according to CNN. Each layer has distinct properties in terms of composition, state of matter, and temperature. Here's a comparison of 4 main layers of the Earth. 1. Crust. Composition. Primarily silicate rocks. State. Solid. Temperature. Varies but generally cooler than the deeper layers. Thickness. Relatively thin, ranging from 5 to 70 kilometers. Significance. The outermost layer where life exists, and it's broken into tectonic plates. Number 2. Mantle. Composition. Primarily composed of iron and magnesium rich in silicate rocks. State. Mostly solid but within a very viscous flowing asthenosphere. Upper mantle. Temperature increases with depth, reaching very high temperatures. Thickness. The thickness layer making up to 80% of the Earth's volume. Significance. Convection currents in the mantle drive plate tectonics. Number 3. Outer core. Composition. Primarily liquid iron and nickel. State. Liquid. Temperature. Extremely high temperatures estimated to be between 4,500 degrees Celsius and 5,500 degrees Celsius. Thickness. Relatively thick with a depth of approximately 2,300 kilometers. Significance. Generates Earth's magnetic field through the movements of liquid iron. And number 4. Inner core. Composition. Primarily solid iron and nickel. State. Solid. Temperature. The hottest layer with temperatures estimated to be around 5,400 degrees Celsius. Thickness. Approximately 1,230 km radius. Significance. Extremely high pressure keeps the iron and nickel in a solid state despite the high temperature. Understanding the Earth's internal structure helps us explain the natural process that shapes our planet. From earthquakes and volcanic eruption, the movements of the continents, and the magnetic field. Each layer has a specific role and character working together like parts of complex machine. By learning what lies beneath our feet, we gain a deeper appreciation on Earth's power, its history, how to protect, and how it goes. Now you know, the Earth is like a giant layered puzzle. Each part helps our planet the way it does.